Shoemaker Levy 9 delivered a rain of chaos onto the cloud tops of Jupiter's southern hemisphere.
Infrared simulation.
Blast zone plumes smeared across the planet's face like campfire smoke caught in thunderstorm winds. It was months following the impacts until most of the debris cleared from cloud tops, washed over by the gas giant's relentless atmosphere.
Simulation. Earth encounter.
Had these celestial bombs fallen to Earth, they would have decimated the planet. But Shoemaker Levy 9 may be one of the best demonstrations of Jupiter's great contribution to life on Earth. Jupiter's massive gravity field may be the solar system's vacuum cleaner that kept our own planet relatively impact-free and allowed life to evolve. Jupiter's existence may enable us merely to exist.
Orbital census underway.
Jupiter's massive gravity well holds more than 63 moons in orbit. It's a symphony conductor, commanding delicate, temperamental strings in the front and more sedate, tractable circuits in the back.
Analysis complete.
Many of these worlds themselves are realms of mystery and wonder. Close to the giant, moons move at tremendous velocity, some zipping around the planet several times in a single Earth day. Further out, the crowd thickens. Moons occupy orbital tracks approximately 20 million miles above the planet. The farthest ones may take more than 2 Earth years to make the elliptical trip.
Referencing subcategory.
But the big, famous ones travel in close. Here's Io. Jupiter's violent gravitational tides push and pull Io's fragile structure. In response, the moon blasts angry bursts of volcanic fire above its blasted face. The big moons are all different too, siblings circling their parent. They exhibit diverse character, from rocky surfaces to odd dented shapes, to places beckoning explorers to pay a visit. Like this one, Europa. Mysterious Europa may hide oceans, tantalizing us with the potential for life. Lines on the surface are really cracks in thick ice, suggesting fluid seas hiding more than 2 miles below. Here's another, Ganymede, orbiting a little more than 500,000 miles from Jupiter. It's the largest moon in the solar system, bigger than even the planet Mercury. In a similar orbit, we find a place of quiet beauty. Sleepy Callisto shows the weary signs of age-old craters. It's an icy jewel, a silent dolmen bathed in reflected Jovian light.
Recomputing standard references. Index complete.
Jupiter, giant of the solar system, capturer of the imagination.
Systems nominal.
It is the Kilimanjaro to the wide open spaces of our solar system, and it pulls our curiosity and attention like a beacon when we look out into the darkness of space. Jupiter, King.
Standing by for new coordinates.
Different satellites to look like the Earth on a typical day. The vegetation detail comes from the MODIS sensor, and the clouds are a composite of 3 days visible cloud imagery taken in 2001. For most of us, this is probably the closest we'll ever get to being an astronaut in outer space, looking back at the Earth. You are now looking at a computer-generated picture of the Earth's topography and bathymetry developed by NOAA. The computer uses color to distinguish features on the planet. On the land, the color gray and red represent the highest mountains, with yellow and green being the lowest points on the land. In the ocean, The light blue colors represent shallow ocean and continental shelves, while the very dark blue represents deep oceanic trenches, miles below the sea surface. It is well known that the land of the Earth contains many mountains and valleys, but what is less well known is that there is a tremendous amount of terrain under the ocean. The Mid-Atlantic Ridge is a striking feature that splits the Atlantic Ocean down the middle and is in fact the planet's longest mountain range. Liquid hot magma is constantly being pushed up from the planet's core along the Mid-Atlantic Ridge, creating the mountains and seafloor. This perpetual yet slow process is making the Atlantic Ocean wider at a rate of 2 inches per year, and at the same time pushing the American continents further apart from Europe and Africa. Also, notice the dark blue indicating deep trenches in the Atlantic and Pacific Oceans. The Marianas Trench, located in the West Pacific near Japan, is nearly 6 miles deep and is the deepest part of our planet. There are many such features to be found in the ocean and appear on this visualization as fracture zones, or things that look like scratches on the ocean floors. Many of these visible features are the results of tremendous and ongoing plate tectonic forces that have shaped our planet over billions of years.
Now please walk slowly to the other side of the sphere for something completely different.
Here, on the dark side of the Earth, are the lights of the Earth at night. This data comes from a network of polar orbiting satellites in the Defense Meteorological Satellite Program. These satellites circle the planet at tremendous speeds between 8 to 15,000 miles per hour. The satellites take pictures constantly as they pass over the Earth, and scientists and computers process this collected data. There are 3 kinds of lights shown here, which represent 1 year's worth of data collection. The white lights are generated by electric sources. The yellow lights are from fires, and the green lights are from fishing fleets. The fires in Africa are caused by burning the fields and grasslands to replenish the nutrients in the soil for growing crops. In the United States, you can see how the lights show the paths of the interstate highway system. We have developed so heavily along these highways over the last 30 years that they are now visible from outer space. Also note the heavily populated areas along the coasts in Europe and elsewhere around the world.
An ocean current is a continuous movement of water. Currents are created by wind, gravity, or differences in temperature and salt. The colors on the globe show different speed. Blue areas are slow-moving currents. Green areas are faster, and the yellows and reds are moving even faster. Ocean currents move warm water toward the poles and bring cold water to the equator. These warm and cold water currents have huge impacts on local and global climates and balance Earth's overall temperature. Also watch as ocean currents hit coastal regions. Small whirlpools called eddies form. Eddies can also spin off the edges of ocean currents. Today, hundreds of Earth-observing satellites orbit high above the Earth. The data received from these satellites provides meteorologists and scientists valuable information to better understand weather and climate. The most common satellites have either a geostationary or polar orbit. Geostationary satellites hover 22,300 miles above the Earth, while polar orbiting satellites fly pole to pole at a height of 450 miles. Watch as the 4 different colored polar orbiting satellites travel around the Earth. The blue satellites are used by the National Weather Service. The red satellites are used by NASA, and the yellow ones are used by the U.S. Defense Department. The smaller white satellite is the International Space Station. It may look like the satellites are crashing together, but each of the polar orbiting satellites fly at a slightly different height.
Now, let's take a look at an X-ray image of our Sun, which allows us to see its outer atmosphere called the corona. The corona is where the solar storms are occurring, those white flashes you see periodically. This dataset is derived from a sensor located on the NOAA GOES weather satellite. The Space Environment Center in Boulder, Colorado uses such images transmitted every minute to predict the weather in space caused by the sun. Solar storms, such as flares, solar eruptions, and coronal holes, can cause interruptions to our satellite communications, navigation, power line transmissions, and space travel. It takes only 8 minutes for a surge of increased radiation to reach the Earth from a solar storm. Like the Earth, the Sun also rotates, on average every 28 days. That's an average because the Sun rotates faster at its equator than at its poles. And that's possible because the Sun is a big sphere of hot gases and nuclear reactions, constantly changing. If this were the actual size of the Sun, how big would the Earth be in comparison? Well, the Earth would be about the size of a nickel. Before leaving this image of the Sun, you should know that this dataset is actually a duplication of the same Sun image on the two sides of the sphere, as there are no satellites on the opposite side of the Sun to take its picture. Here is our nearest planetary neighbor, Mars, as seen by a NASA satellite. Mars rotates on a tilted axis of about 25 degrees, meaning Mars has seasons, just like the Earth. Other similarities include land features such as canyons, mountains, and polar ice caps. If you've been to the Grand Canyon, you know that it is very deep. It is actually more than 1 mile deep and over 200 miles long. On Mars, notice the long gash in its southern hemisphere. That is the Mariner Valley. It is over 2,500 miles long and 5 miles deep, a canyon that would stretch across the United States. Now, look to the left of the Mariner Valley to see an example of a Mars mountain. That is Olympus Mons, an extinct volcano. It is estimated that Olympus Mons grew to well over 85,000 feet before it stopped erupting. By comparison, Earth's Mount Everest is around 29,000 feet, but it's still growing due to the push of plate tectonic activity. The recent exploration by the NASA Mars rovers seems to support the idea that there was once a great deal of water on the Martian surface. Scientists have long speculated that the lower elevation northern hemisphere once held vast oceans. At the poles, there are still ice caps consisting mainly of frozen water, but they are relatively small compared to the Earth's Antarctic ice cap.
Signal acquired. Now receiving data. Subject, fifth planet, gaseous.
This is the biggie, the heavyweight, the giant. Jupiter, largest planet in the solar system. So let's get the obvious question out of the way. How big is it?
Analyzing.
This is Earth. This is Earth compared to Jupiter. It would take more than 1,000 Earths to fill the fifth planet. But our journey today fixes a bullseye on Jupiter.
Referencing data index. Telemetry archive online.
Most of the images you'll see come from various spacecraft that made the trip.
Data now available.
For example, Voyager 2 collected this remarkable sequence in 1979. Movies of Jupiter are exceedingly rare.
Approaching Perry axis.
Most visiting spacecraft simply use Jupiter's immense gravity as a slingshot for journeys elsewhere.
Low gain antenna online. Spectral analysis complete.
Churning skies of roiling clouds compel the attention of even casual visitors. Jupiter's face is an opaque, seething mask, ever-changing revealing nothing of the small, dense core, tens of thousands of miles below.
Hydrogen, helium, atmosphere.
The planet's extraordinary rotation speed keeps the grinding sky in constant motion. The huge planet makes a complete revolution in just 10 hours,
Enhancing image.
compared to 24 on our little Earth. Winds howl constantly at almost 300 miles per hour.
Vector analysis.
With that much wind, strange things are bound to blow around.
Atmospheric anomaly detected.
Like this, the famous red spot. The red spot is a rotating high-pressure system, weather, in other words. And it's a storm that's been churning for well over 100 years, likely observed in even the earliest telescopic observations of the planet. Just like our own planet, Jupiter changes every day.
Deep space object detected on convergent vector.
In July 1994, the comet Shoemaker-Levy 9 fell into Jupiter's gravitational thrall.
Tracking